Hi, welcome back. Today I am here with another module of simulation in R. In this module, as we have discussed earlier, we are going to discuss about several examples with considering simulation in R. Here, at first we are going to discuss about some very simple example of how binomial distribution tends to Poisson distribution. Then we will be discussing about how simulation is applicable in order to prove law of large numbers, and in the last part of the module we are going to discuss about how T confidence intervals can be simulated by constructing a simulation study. So, let us see what is there in this module. So, here as we have told, we are going to consider a number of examples. The basic objective of us is to elaborate the aims and objectives that we have started earlier with. So, here in course of doing that, let us talk about an example which is very simple, but indeed very appealing. The example tells about the Poisson approximation to the binomial. Now, by now all of us is aware of the cases when binomial distribution tends to Poisson. What actually is it? It tends when suppose x follows binomial with parameters n and p, which is the standard one. As we know here, n is the number of trials and p is the probability of success. Then if the number of trials, that is n, tends to be a large number and simultaneously the success probability p tends to be small, and at the same time if lambda, which is the parameter of the Poisson distribution and also the mean and variance as well. So, when this equals NP, that is when lambda is equal to NP, then under these many conditions binomial distribution tends to Poisson distribution, that is when n tending to infinity, p is very small and lambda is equal to NP. Now, let us try to find how R helps us to visualize this. Suppose we are flipping a coin substantially many number of times, say 600 times, and the probability of getting a success has been fixed to be 0.01. So, as we know here n equals 600 and p equals 0.01 for a binomial random variable. Now, here we are trying to find the probability less or equal to 2 for a binomial distribution. So, here we are using the command p binom, then within first bracket 2 comma size is equal to 600 comma probability is equal to 0.01, as we know that, and we are having the probability to be 0.06107634, as you can see this from the slide as well. Now, what we are doing is that we are taking this n and p and multiplying it and using it as lambda, since lambda is equal to np. Now, but this lambda will be used and how? This is the question here. As we know, we are using this again to find the probability less than or equal to 2 for a Poisson distribution. So, basically we are wanting to have the distribution function of a Poisson distribution here with the command ppoise 2 comma lambda is equal to n into p, that is 600 into 0.01. Now, here since n is sufficiently large and on the contrary p is sufficiently small, so we can use this, and let us look at what we are having here actually. Using the binomial code, we are having the cumulative probability to be 0.06107634, that is the one we have given here, and using the Poisson code what we are having is that we are having 0.0619688. And these two are approximately the same, as it is pretty obvious from the output. We can just tell this after looking at this. So, here as we have discussed earlier, mathematically we all know how to prove this, but that involves some approximations and detailed calculations. But the way we are getting this here is really very simple, less involved mathematically, and this requires much lesser amount of times that are required here in case of theoretical approximation. So, it needs a lot lesser time compared to the theoretical approximation. Now, as we can guess that the law of large numbers can be explained explicitly by the help of a simulation study. So, let us start doing this and let us find whether the thing that our intuition tells that matches with what the actual situation is. So, what does the law of large numbers say? It primarily gives us the large sample behavior of sample means of a collection of IID observations. As it says, to be more specific, if we flip a coin again and again and then suppose we calculate the average of the results of these n experiments, which can be x n bar. In our case, x n bar is the proportion of heads of successes, that is for the case of flipping a coin. Then as this n or the number of coin flips increase, then this x n bar will actually tend to the true probability of a head. So, as we can see, it requires lots of coin tossings of better understanding. So, we can surely visualize this with the help of a simulation study. We can guess that. So, let us see how it works and how it does the whole thing, how we can do the whole thing with the help of a simulation study. So, here as you can see, we are starting with 1000 observations. So, n is taken to be 1000 here, which is indeed substantially high, we all know that. Now, what will we do? We will generate n random numbers from normal distribution and taking the cumulative sum here. As you know, we can do this by using a loop as well, but since we have a built-in function here, so why not we use this? So, here we are using this and having our cumulative sum as it has been written here. Now, we are trying to find the cumulative mean, because remember, this is the thing which we require to have the flavor of what the law of large number actually is. So, basically, as the cum sum SUM gives the sum of the consecutive observations, similarly, we are calculating the mean of the first observations, which is the observation itself, then the mean of the first two observations, then that of the first three observations, and so on. So, by this way, we are having this SUM, which is cum sum, and we are storing this thing within the variable AVG, that is the average, and here our average, here this is our average variable. So, now we are plotting the cumulative means corresponding to the observations. So, with the help of this code that has been given here, our plot will look like this. Have a closer look at the plot. Here at the very beginning, there is a lot of variability on the mean, but as the number of simulation increases, we are having a different story. Here, with the increase in the number of simulation, the cumulative means tend to stabilize around its true value. Here this is 0, as we know, as we have started with 0. So, the picture is echoing the same thing that had been explained earlier by the law of large numbers. So, as we can understand, simulation is something which can explain a lot of theoretical aspects of statistics which can otherwise be at times quite difficult to handle. Here we are doing the similar kind of thing, but instead of taking a sample from a standard normal population that we have done earlier, let us try something new. Here we are flipping a coin and trying to see what is actually happening in the long run. So, let us concentrate on this. So, instead of the rnorm command, we are using the sample function here. Here we are writing sample, then within the arguments 0, 1, comma n, then replace is equal to true. By the argument 0 and 1, we mean that it samples from either 0 or 1 with equal probability. Then the argument n denotes the simulation size, that is the number of times we are sampling. Now, as we are flipping a coin again and again, here the head is denoted by 0 and the tail is 1 with equal probability, and since we are dealing with an unbiased coin, so the probability of head is equal to the probability of tail. So, the head is denoted by 0 and tail is 1, and replace equals true implies we are executing with replacement sampling, which is the case of coin tossing as well. We will discuss about the sample function more explicitly later. Now, again, like the case of the previous one, here as well we are taking the cumulative sum of these samples of 1 and 0 and dividing them with 1 to n. Here we are actually having the cumulative means of the results of the coin flips, and we are storing these values within the variable AVG. Again, to plot the cumulative means against the number of observations, we are using the command that is given here. So, using the command, we are having this plot. Now, looking closer towards this plot, we are coming up with almost similar ideas that we have got earlier. Here also, in the very beginning, the sample mean fluctuates, but as we increase the simulation size, then they tend to stabilize around certain value. So, what is the value? In the previous case, since the true underlying distribution has mean 0, so it tends to stabilize around 0. Here, remember, we had started with an unbiased coin which has 0.5 as the probability of getting a head. So, as the simulation size increases, the sample proportion converges to the true value, which is 0.5 here. Now, let us take up something about confidence intervals. For this, let us consider an example of simulating T confidence intervals. Let us see how we can deal with this particular problem. For this, let us start with some samples. So, the question is, how do we get those samples? Here we are drawing these samples from a standard normal distribution. The reason is clear to you by now. The simple reason is that primarily we are dealing with small samples, and also we are wanting to see the confidence interval of a T distribution. That is the reason why we are taking up the underlying distribution to be a normal one. Now, let us focus on how the simulation study will be executed. Here primarily we take up samples of size 10 each from a distribution which is a normal one, as we have just discussed. The next thing that we would do is we will repeat it a number of times. Let it be k. For each of the cases we will get the confidence intervals. Now, when we talk about confidence intervals, we state that the estimated value of the parameter will lie within this interval that we have specified with a certain probability. So, this means there might be a few cases for which the confidence interval is not going to contain that true value. So, let us try to capture those cases. How do I do this? Let us see. So, as we have said, we have taken k samples each of size 10. Now, we are counting the number of instances for which the confidence interval includes the mean. Remember, what is the mean here? As we have generated sample from a standard normal distribution, so the actual mean is 0. Here, we are assuming the mean to be unknown and wanting to test whether it is around 0 or not. And also, the standard deviation is unknown. So, as we know, the distribution of the test statistic is t with the degrees of freedom equals the sample size minus 1, and we are having a two-sided confidence interval in this case. So, here we are having our alpha to be 0.05 and the sample size, which is denoted by n here, has been fixed to be 10. So, in the very beginning we are getting the cutoff points of the t distribution. Usually these are said to be the tabular value, but these are available from the tables. But now the softwares including R provide these values, so it makes the work more simpler. So, let us use this. So, we are having the cutoff points for the t distribution with arguments alpha by 2, degrees of freedom to be the sample size minus 1 and many more. We have discussed these things earlier as well. So, these values are stored within the t alpha by 2 variable, and here it is. Now, here let us have some recapitulation of what you must have learnt during your inference course. You know that the confidence interval for mu is x bar minus t alpha by 2 into s by square root of n and x bar plus t alpha by 2 into s by square root of n. So, it is basically x bar plus minus t alpha by 2 into s by square root of n. So, this is a case where the parameter will be included in the confidence interval, but as we have discussed, there are cases where it does not include that, and we know what actually it is. So, let us consider this. We know that mu is equal to 0 is out of, for mu is equal to 0, then the parameter will be out of the confidence interval if x bar square is, or x bar minus mu whole square is greater or equal to t alpha by 2 whole square into variance by n. Just squaring this term, we can get this. Now, since we can understand that we are dealing with this thing only where the parameter mu is out of the interval, so we should concentrate on this thing only, this condition only. The condition we have just stated, that is x bar square is greater or equal to t alpha by 2 square into variance by n. So, let us think of how to minimize our effort. Here mu is equal to 0 always. So, we are putting that thing here. Now, x bar will vary with the varying sample. So, we cannot fix it, and also the variance will vary as we draw a new sample. So, we can't fix that as well, but what we can fix is the remaining part, which is t alpha by 2 square by n. So, let us fix it and let us name it to be C. Now, look at the R code that we have given here. This basically tells the whole idea of the program. Here, as we can see, we are starting with k is equal to 10, which means the simulation size is, we are starting with k is equal to 100, which means the simulation size is 100 here. That means we are drawing the sample of size 10 each 100 many times. Next, we are fixing the variable count to be 0. This is a variable which actually counts the number of times where the confidence interval failed to contain the value of the parameter. Next, what we are doing is, as it had been told earlier, we are drawing 10 random values from the standard normal distribution and storing them within X. So, here is our X. Now, again, as we have discussed about the formula, we are just following this here. So, if the mean of x squared is greater or equal to C into variance of X, in that case the confidence interval is not going to contain the value, and hence we are counting it to be a failure, and we are increasing the variable count by 1 in these cases. So, the count variable is basically counting the instances of failure. So, here is our count variable and it gives the value 4 here. Now, think of what does 4 means, what does the output means? It means that out of 100 samples of size 10, the confidence interval cannot capture the mean 4 times. So, the proportion of interval failing to capture is 0.04, as we can understand. If you repeat this whole thing again and again for the same simulation size, that is, if k is equal to 100, then we will be having the values of the variable count to be 7, 6, 5, 4 in the consecutive repetition. So, by now we have a clear idea regarding what is actually happening here. Now, let us do some more experimentation with this. Next, we are trying to increase the number of simulation, and let us see what happens here. Here we are replacing the value with 1000 and letting the other things exactly the same, what it used to be. Now, let us see how it goes. Here we are having the value of the variable count to be 52. So, what does it mean? We have seen similar kinds of thing in case of k is equal to 100 as well. So, comparing them, we can infer that out of 1000 samples of size 10, the confidence interval is unable to capture the mean 52 times. So, this is what we are getting here. Now, as we have told earlier that we will increase the simulation size. So, we are doing exactly that thing here only. Here we are taking the simulation size, that is k, to be 10,000, and look at this. This is what we are getting here. Here the count is found to be 516. Keep on doing the same thing of experimentation with varying k again. Here k equals 1 lakh, and look at what we are getting here, what the count actually is here. Here it is actually 5004. So, as we know, it gives us the fact that out of 1 lakh samples of size 10, the confidence interval is unable to capture the mean 5004 times. So, we can continue doing this with increasing simulation size, but let us stop here and start something which is more interesting visually. Look at the plot. Here this is diagrammatic representation of what we had been talking about so far. The plot says all the things. The cases where mu is captured are denoted by the green lines, and those which do not contain mu is equal to 0 is denoted by the red ones. The diagram is basically based on 100 simulation each of size 10, and here, as the plot suggests, that out of 100 cases we are getting 8 many cases where the confidence interval is unable to capture the mean. So, this is what we are actually getting within the plot from. Now, we can have different plots with the increasing number of simulation size as well. We can always do that, but we are not doing it here since they would make the plot clumsy and hence difficult to interpret. So, we are explaining with taking simulation size to be 100. So, we have started with the basic aims of simulation. we partially fulfilled our aims or objectives by now. We have come across a lot of interesting problem here. There are many of the problems of this kind which are yet to come across. These are all about experimenting with the conventional theoretical statistics that we have studied till date. It's all about how we can explain the things which could otherwise be explained in a complicated ways. Like we all know that for small sample case t-test holds when we have taken the underlying distribution to be a normal. But can you simulate a random sample and can you show how this holds? So, these are basically the things which are yet to be done by you. So, start doing this experimentation from now on. So, we have discussed about 3 of the examples here, and as we can see, through simulation study, these kinds of theorem can be proved here. Otherwise, if you want to prove this mathematically, then it will be very involved and it will require a lot of mathematical expertise, or it will require a lot of time. So, through simulation studies we can avoid all these kinds of things. So, that is why we always prefer such kinds of simulation study. Also, you can always keep on experimenting with such kinds of theorem, and you can use these kinds of simulation studies as well.